Hi, guys. We are going to move into chapter 9 and chapter 9. So, a lot happening in this section, a lot of important stuff. We are using properties of radicals in this section. So, just a reminder here, when we are simplifying a square root, okay? So if we're simplifying something like the square root of 28 or the square root of 50, we looked at a couple different ways that you can go about doing it. The two main ways that we talked about were the killing twins method and then finding the largest perfect square that goes into it. Okay, so we're really going to focus on both of these two methods in here. All right. And when we had both of those two methods, remember when you do the killing twins method, which is example 2 here, we create a factor tree, and then we put all of the factors underneath the square root, and we find any twins, we kill the twin, and then that remaining twin moved to the outside, and we get an answer such as 5 root 2. In the square factor, that's when we have to find the largest perfect square that goes into that square root. So for example, 45, the largest perfect square that goes into it is 9. So then we break it up into the square root of 9 and the square root of 5. Square root of 9 is 3, so we end up getting 3 root 5. If you're going to use this technique here, it's important that you know your perfect squares, which are listed over here. In the killing of twins method, you don't need to know your largest perfect square. You can just create a factor tree. But those are your two techniques that you can do when you're simplifying a square root. Okay? And this is what's shown as this core concept here. So let's take a look at the square root of 108 and see how we can deal with that. So if we look at the square root of 108 and we'll do it both ways here. So let's first do it by doing the largest perfect square that goes into that. So then I have to think to myself, okay, what are my perfect squares? Well, I've got 2 squared, which is 4. I've got 4. I've got 9. I've got 16, 25, 36. And I have to find the largest one of those that is going to go into it. And if I think about that, the largest perfect square that's going to go into that is 36. Because 36 times 3 is 108. So I divide it up into the square root of 36 and the square root of 3. Square root of 36 is 6. So I end up just getting 6 root 3 as my answer. That's the largest perfect square technique. The other way you can do it is by finding the killing of twins technique, where you just take this and you create a factor tree. And it doesn't matter what you divide by first. So I might divide by, say, 2 first, because I know 2 goes into it, and 2 is a perfect square. 2 and 54. And then I can divide 54 up into, say, 9 and 6. Well, where can I go after this? Well, 9 could be 3 and 3. And 6 can be 2 and 3. So when I use the factor tree, I have to get them into prime numbers. So once all of these numbers here, don't forget about this guy up here, are prime numbers, then I write everything underneath the square root. So underneath the square root, I've got a 2. I've got another 2. And then I've got 3 3s. When I use the killing of twins technique, this is the killing twins, we're getting violent. What I do from this point is, I look at any twins that I have. Here's a set of twins. This is actually triplets, but I don't care about when I'm doing a square root triplets. And I go here. What happens? One gets killed. The other one runs on the outside. So I have a 2 on the outside. Same thing here. Gone. This one goes on the outside. So this and this have all been taken care of. All that's left is that 3 on the inside of the square root. What's left on the outside? 2 times 3, which is 6. So I get that same answer of 6 square root of 3. So yes, in this particular problem, the square root technique was quicker. But you have to know your perfect squares to use that. I'm going to do this one on here. Because now, if I think about this, I've got 9 and then x cubed. So I'm going to kind of do like a hybrid method here. I know that the square root of 9 is just 3. Now, what about the square root of x cubed? Well, if I think about that, the square root of x cubed is really x times x times x. So what happens there, if I use my killing of twins technique here, is I've got a set of twins here, gone. On the outside, I have an x. So I have an x on the outside, and then what's left is an x here on the inside of my square root. So I end up getting a final answer of 3x root x. And again, there's different ways you can go about doing this, but that's how I would do that one. And this just goes through breaking it down as well. Same idea on these, okay? If we want to take a look at one or two more of these, like for example, let's do this one because it's a little bit tricky. So that square root of 75, if I want to use the largest perfect square, I know 25 goes into it, and I can do 25 times 3. So now this gives me 5 root 3. I'm going to kind of use killing of twins here. N, 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 and N. So what happens here is, here's a set of twins, here's a set of twins. Gone, gone, outside, outside. So I end up getting N squared, N. So if I combine both of these together, on the outside of my root, I'm going to have 5n squared. And on the inside, I'm going to have 3n. And that would be my final answer. This is easy because this is perfect square. So this would be 7x root x. All right, now we're going to be dividing square roots. So now we have the quotient property of square roots. When we have the quotient, okay, meaning we're dividing two values and both of them have squares, we can rewrite that as two individual squares. So the square root of 3/4 is equal to the square root of 3 over the square root of 4. Okay? And then we can simplify from there. So if we have the square root of 15 over 64, this could be equal to the square root of 15 over the square root of 64. Well, 64 is a perfect square. It's equal to 8. So I'd get an answer of square root of 15 over 8. Here, we can have square root of 81 over the square root of x squared. Square root of 81 is 9. Square root of x squared is x, so I would get an answer of 9 over x. And this just shows them here. Now we're moving on, and now we're not doing square roots. We're doing cube roots. So now you need to know your cube roots. So two ways, again, to think of it. You could think of your perfect cubes, which is 2 cubed, which is equal to 8. 3 cubed, which is equal to 27. 4 cubed, which is equal to 64. 5 cubed, which is equal to 125. 6 cubed, which is equal to 216. Okay, and that's probably all you need to know. So if you're going to use this technique, again, you could go ahead and find the largest perfect cube. So for example, here, if I say negative 128, I know 64 goes into that, right? So I could take this cube root of, and I'm going to take negative 64, and then I could take the cube root of 2, because 2 times negative 64 is negative 128. Well, the cube root, and again, this is important, cube root of negative 64 is negative 4. And then I can't do anything with this, so then I have negative 4. That's a 3. Get that clear. Oopsies. What are you doing here? There we go. And there's my answer. That 3 is the index. Okay? Now, you can also kill triplets if you wanted to. So if we want to take this 128, and I want to divide it up, I might do 2 and 64. 2 is a perfect square. Then maybe 8 and 8. Then maybe 4 and 2. There's a 2. And 2 and 2. And same thing here. 4 and 2. And 2. And 2. And then all of these 2's, how annoying, are going underneath the square root. So 2, 2, 2, 2. How many do I have here? 1, 2, 3, 4, 5, 6, 7. So 7 of them. 2, 2, 2. Now I'm looking for triplets here. Why? Because it's a cube root. So here's a set of triplets. Here's a set of triplets. Now when you're dealing with triplets, you got one really evil triplet. He gets rid of both of these guys. And he goes on the outside. Same idea here. Gets rid of both of them, and then he goes on the outside. So what are you left with? A 4 on the outside. What do you have on the inside? Just that lonely 2 right there. It's a cube root, and it was a negative. So we get -4 cube root of 2. Same process, though. Same process. Let's do perfect cube form here. Well, I know the cube root of 125 is just 5. So that will get me just equal to 5. So I've dealt with that. Now I have to deal with the cube root of x to the 7th. So if I think about that, and again, I'm sort of going to use this killing of twins technique here, because I have x times x times x times x times x. I've got 7 of them times x. How many is that? That's 6 times x. Well, how many set of triplets do I have here? Here's a set. Gone, gone. Goes to the outside. And here's a set. Gone, gone. And he goes to the outside. So on the outside, we're going to have x times x. On the inside, we have a cube root of x. So we end up getting x squared cube root x. So when we put it all together with the 5 that we did from before, 5x squared cube root of x as my final answer. Not easy, all right? Let's go here. Here, we've got to break it up into the fractions. So we have cube root of y over cube root of 216. Well, cube root of y is just going to stay cube root of y. Cube root of 216 is one of my perfect cubes, is just 6. So I end up with just cube root of y over 6. Here, let's split it up. Cube root of 8x to the 4th over cube root of 27y cubed. Our numerator is going to become 2x cube root of x. And on the denominator, we're going to be 3y. And there's my final answer. And again, same answers that we just got here. Okay, I don't think we need to go through the try these. All right, they'll be posted, but you'll have them on your own. Now, we have an issue here because what we have here is you cannot have a fraction, or sorry, a square root in the denominator. So no square roots are allowed in the denominator. So in order to get rid of that square root, we have to multiply both the numerator and the denominator by the root. So I have to multiply top and bottom by the denominator. Okay, so we need to multiply by the denominator to get rid of that square root. So when I multiply the square root of 3n times the square root of 3n, the square roots just cancel here. You end up getting just 3n. They don't cancel on the top, and we're left with square root of 15n. Now, the reason that these don't cancel, that they cancel on the bottom, is because you end up getting here when we multiply them, 3 squared n squared, which is just equal to 3n. So that's why this cancels out to just 3n here. And we end up getting an answer here. Now I'm going to multiply here, top and bottom, by the cube root of 9. So what happens here is that these roots will just cancel, and you'll be left with 9 in the denominator, and then 2 cube root of 9 up top, and there's nothing else to be done there. Oops, sorry. You're going to end up with a 3 down here. Okay, next example. We have 7 over 2 minus the square root of 3, and we have to get rid of that square root on the bottom. When you have something like this, you're going to multiply by what's called the conjugate. So what does that mean? That means 7 over 2 minus the square root of 3. We have to multiply this by the conjugate, which is going to be 7, which is, just going to be 2 plus the square root of 3. Now, as you can see here, so I don't have to write it all out, when you have 7 over 2 minus the square root of 3, and now we multiply by the conjugate, 2 plus the square root of 3. In the numerator, you're going to get 7 times 2 plus the square root of 3. So in essence, what you're doing is you're distributing. You're going to get 14 plus 7 over the square root of 3. And on the bottom, what's going to happen is it's going to cancel out to just be equal to 1. So your final answer would be 14 plus 7 over the square root of 3. And that's what we call multiplying by the conjugate. Okay, these are just some more examples, which we'll post. And we're not going to worry about the word problems for now. Oh, but we will do example 8. So example 8 now, you have to simplify the expressions. So now what we have to do is we're just combining, almost like you're combining like terms. So if we notice, these are both like, think of it if it was like 5x minus 8x. So think of the roots as almost like the x's. So you have a 5 root 7 minus an 8 root 7, which is going to get you a negative 3 root 7, plus the square root of 11, and that's just your final answer. Now here, you have to simplify the square root of 20. So the square root of 20, we can simplify to square root of 4 and square root of 5. So this is going to become 2 root 5. So now we have 10 root 5 plus 2 root 5. So we'll get a final answer of 12 root 5. Let's look at one more. Okay. We have 6 cube root of 2, or cube root of x plus 2 cube root of x. That could become 8 cube root of x.